So this is the 2013 Level 3 Waves paper. Question 1. The police whistle. Some police forces have used whistles that have two chambers of different lengths. Copyright. And then a model of the whistle chamber is shown in the diagram below. And then the first question on the diagram above, draw the fundamental standing wave in the shorter chamber and label any displacement nodes and antinodes. So in the shorter chamber, they're both closed at one end and open at the other end. So the closed end by necessity has to be a node. So at that point on the shorter chamber you'll have a node, and then you have an antinode at the open end also by necessity. I'll explain that in a moment. So how we would draw them is usually like that, which is a transverse representation of the longitudinal movement. The longitudinal movement with the node means that it will be zero movement there. You can't have any, remember the movement is going of the air molecules. If we consider a single molecule at that point is going backwards that way and then backwards the other way at a maximum displacement, which is what that vertical is representing. And then at this point here you have zero movement, and that can't move because you've got a fixed end and the air particles can't move to the side, so we don't have that. Anyway, that's what you'd have. That's your fundamental form of the wave. Next one, the fundamental frequencies for the two chambers. 2136 Hz, 1904 Hz. The speed of sound in air is 343 meters per second. Calculate the length of the longer chamber. So the longer chamber will have the higher wavelength, the higher length of the fundamental wave, because remember we have 1/4 of the wavelength in each of these, because the full wave is going to go down and then back if we were to get the full length of the wave, and we've only got that much. So it's 1/4 of the wavelength in here. As I said, the longer chamber has the higher wavelength. From the wave equation, V equals F lambda. The one with the higher wavelength, for the same speed of velocity sound, we'll have to have the lower frequency. For the longer chamber, we're going to use that frequency there. So we know V, we know F, and we're going to calculate the wavelength there. But that doesn't end. We've got to calculate the length of the longer chamber. So we're going to take that wavelength that we get it there, and we're going to divide it by 4 to get the actual length of the chamber. C. Explain how a standing wave is produced in a pipe that is closed at one end. So in a pipe that is closed at one end, there's your closed end. What we would say is probably with the whistle it's resonating the air at the open end. As it resonates the air, it sends a you're displacing the air. You send that non-standing wave. You're sending it down the length of the pipe, hits that end, and then it bounces back. But as you continue to with the whistle, you continue to blow on the open end. You're continually sending that wavelength down, and you're continually having that reflected one coming back in. Now these two waves are interacting with each other, causing constructive and destructive interference at different points. At the nodal point you're going to get destructive interference, and at the antinodal point you're going to get constructive interference, which produces the antinode and the node for those two things. And it's really, I mean, yeah, that's more or less it. You have for a standing wave to be produced, you have to have two waves that are travelling in opposite directions. So two waves travelling in opposite directions, and yeah, I guess there's you're talking about the right driving frequency for that length of pipe, and so in this case the only trick I suppose is that you've got two waves. You've only got one wave, but it's bouncing back on itself to interact with the other one. There may be a few more details that you need for that. I'm doing this question very early in the morning, but you can check it on the marking schedule on the NZQA website in case I've missed anything. D. When the whistle is blown, the sound made is quite different to a pure sound of either 2136 Hz or 1904 Hz. Calculate the value of two other frequencies produced and explain why these other frequencies are produced and what effect they have on the sound. Okay, so we're basically looking at overtones here. Okay, or other harmonics. So we would talk about just in terms of the explanation, we would talk about overtones, harmonics being produced, and the effect they have on the sound. The same fundamental must be existing, so that's still there, meaning the overall the pitch or frequency is unchanged, and we're not going to have any, therefore, different kind of pitch heard, but it's going to affect the timbre. So you'll have a unique sound based on the length because you're adding overtones to the fundamental. So you've still got the basic wavelength of the fundamental being produced, but you've got overtones added on top of that, affecting the waveform and giving you a slightly different sound. So then how do we calculate a different sound? We would have to look at, say, one of the overtones. You do this for both of the, and in this one we have 3/4 of a full wavelength in there. So then we would use the length that was calculated previous. Well, we don't have to. If we've got 3/4 of the wavelength in here, that means we now previously we had 1/4 of a wavelength in that same length of the pipe. Maybe we'll just move down a little bit, give ourselves a wee bit more room. Okay, so change a bit of colour for a bit of fun too. So previously we had 1/4 of the wavelength in there. Now in the same length we would have, trying to draw it fairly consistently, we have 3/4 of the wavelength. So if we go right back to our earlier question B, we calculated the length of the longer chamber. Now with that same length, we could use the same method to calculate the length of the shorter chamber using that frequency, so we can calculate both the lengths. And then in this time we can use that length to find the length of each of the shorter chambers. So we would have the length of the short chamber, length of the long chamber, and that's going to tell us what the wavelength is. So to get the full wavelength for this situation, where you've got 3/4 of the length in there, you would take that length and you're multiplying it by, you're adding a third, I guess, so you'd have times by 4/3, and that will give you your new wavelength. You can use your wave equation, V equals F lambda again, frequency. Your frequency is the one you're trying to find out. So you've got the wavelength and you've got the velocity, and you do that for both of those lengths. There you go.